Alright, so let's say you're given this diagram here of, let's say a guy is trying to push this block up a ramp, and the question says, a guy pushes a crate up a ramp with a force such that the crate has an initial velocity of 5 meters per second. The crate only makes it 1.6 meters up the ramp due to a force of friction. Find the force of friction. To start, we can use the conservation of energy to solve. Note, energy is not totally conserved in the system. It loses energy due to the force of friction. So the usual conservation of energy equation is given here, but we need to add the contribution from friction. If we identify E1 at the bottom of the motion and then E2 at 1.6 meters, E1 equals E2 is still going to hold from the fundamental property that energy cannot be created or destroyed, only transferred. So at E1, the energy is still going to be the same. It's going to be the kinetic energy plus the gravitational potential energy. We can plug in our known values. H1 is going to be equal to 0 meters in this case because the object's at the bottom. The initial velocity is 5 meters per second and the mass is 12 kilograms. So our potential energy is going to be 0. We're just going to have our kinetic energy term here. We compute the amplitudes into units and we get this. Note, all the energy at this point is kinetic energy, and this makes sense because the contribution from gravitational potential energy is 0 since the object's at the bottom. Energy at point 2, it's going to be the potential plus the kinetic, but there's also going to be a negative work other term since the system loses energy throughout the motion. The friction force is going to be doing negative work on the object. We can identify work other as work friction. And our general work equation is force times displacement, where F is the force, in our case is friction, and delta S is the displacement. And it could also be written in this form here where theta is the angle between the friction force and displacement. We can plug these values in and then we can identify H2 is going to be this height here, which depends on the 30-degree angle and 1.6 meters. So if we use trig, we can identify that H2 is opposite to the angle, so it's going to be sine theta. H2 is going to be 1.6 sine 30 degrees, and if we plug that in, we get 0.8 meters. Final velocity is going to be 0 because it says our object comes to rest. Our friction is unknown, and then our displacement is going to be along this line here, so it's going to be 1.6 meters, and it's going to be pointing in this direction here. For theta, the force of friction is pointed in this direction here, so we can draw an angle between the force of friction and delta S. It's going to be 180 degrees. So we can plug all these values in, and then we can cancel out the 0 term, which if we do that, we get this, and then we can compute the amplitudes in units of the left term and the right term, and then we get this expression here for the final energy of the system. So to find friction, we know that energy 1 is equal to energy 2, and if you remember, we solved for energy 1 up here, so we just plug that in, and then we plug the expression in for E2. From here, we can isolate for friction by bringing the first term to the left-hand side, and then doing a simple subtraction. And then we can multiply the expression by negative 1 over 1.6 meters. We cancel the negative 1.6 meters on the friction term. We're left with this here, and then we can compute the amplitudes in units, and we get this final answer. This is the friction that is felt by the object that causes it to stop